Welcome to the lecture number 32 of the course Stochastic Hydrology. If you recall, in the last lecture we discussed essentially about the principal component analysis, but as a prelude to preparation to the principal component analysis, we discussed some basics of the matrix algebra, especially dealing with the eigenvalues and the eigenvectors. Now, for a square matrix, we saw that the eigenvalues can be got by determinant A minus lambda I is equal to 0, where A is the square matrix for which you need the eigenvalues and lambda are the eigenvalues and I is the identity matrix. Now, once you get to the eigenvalues, you can also go on to get the eigenvectors by putting A x is equal to lambda x, where x become the eigenvectors. If you have the matrix A of size n by n, then you will have n eigenvectors corresponding to the n variables of the A matrix. Then we went on to do the principal component analysis, where we express z is equal to x A, where z is the transform data, x is your original data. If you have p variables and each of the p variables having n observations, then this will be of the size n by p, and A is a vector of A is a matrix consisting of the eigenvectors. So, you will have p by p size. So, that is how you get the transformed data z. Now, this is what we did in the principal component analysis. Towards the end of the principal component analysis in the previous lecture, I mentioned that there are advantages of dealing with the principal components when we are regressing using the regression with multiple variables, large number of variables. And the typical example that we provide in hydrology is, let us say the runoff at a particular location is dependent on several rain gauges, several rainfall values in the catchment, and then apart from the rainfall values, it may also depend on other variables. For example, it may depend on the soil moisture, it may depend on the vegetation, it may depend on the area of the catchment and so on. So, there are several variables on which the runoff is dependent, and you want to develop a regression for the runoff in terms of all of these variables. There are two features in this particular exercise. One is the number of variables themselves, number of variables itself is large. Let us say you may be dealing with 10 variables, 12 variables and so on, with each of the variables having a large amount of data. Let us say rainfall at the location you have 50 years of data. Similarly, runoff you have 50 years of data, and rainfall may be for several locations. At each rain gauge you may have 50 years of data. So, the size of the problem becomes large when you are dealing with large number of variables and large amount of data. Additionally, many of these variables may be correlated among themselves. As I mentioned, if you are looking at soil moisture and rainfall together in the regression model as independent variables, the soil moisture and rainfall themselves will be highly correlated. So, to account for these correlations, essentially to remove these correlations among the independent variables and to reduce the size of the problem, that means instead of dealing with 10 variables, I may want to deal with only 3 variables. To achieve this purpose, we carry out the principal component analysis. So, there are two major advantages of the principal component analysis. One is the original set of correlated variables are transformed to a set of uncorrelated components, and this is a linear transformation of the original variables. And in doing so, what we are also doing is that we are identifying which of these components explains most of the variance present in the process, and therefore, we can afford to choose only a few of the principal components and ignore the remaining. So, what was a regression of on 10 variables may now be reduced to a regression only on 2 variables, although these 2 variables that we are now dealing with will not be directly related with the original variables. They are some kind of a linear transformation of the original variables. So, the original variables would have lost their identity. In the final regression, we may not be able to say that the first component is in fact rainfall, second component is soil moisture and so on. Both these components will be a linear combination of all the variables that we considered earlier. So, we will progress now and see how we use the principal components in the regression. Remember, our idea is to develop a relationship between the dependent variable, let us say the runoff, and the set of independent variables which we have identified based on the physical processes that govern the runoff process. And we have the data on all of these variables. On dependent variable we have and concurrent values of the independent variables. Concurrent because we are saying that the rainfall during that period, let us say you are talking about a month's time period, rainfall during that month produces the runoff during that particular month, and therefore, you should have concurrent values of all of these variables, dependent variable as well as all the independent variables. On the independent variables, we do the principal component analysis. In the last lecture, I introduced how to do the principal component analysis on any sets of variables. So, on the independent variables now, we carry out the principal component analysis. What is the idea? The idea is again that we want to transform this set of independent variables independent in the sense that they are independent of the dependent variable, but among themselves they may be correlated. So, we want to transform this set of independent variables x 1, x 2, x 3 etcetera up to x p into another set of variables which we call them as principal components by using the transformation, and that is what we do, and then regress the dependent variable now y with respect to the principal components and not with respect to the original variables, and that has several advantages. Let us see. So, essentially regression on principal components is necessary because we want to develop a stochastic model on the dependent variable using all these independent variables. And to the derived principal components, as we derive from the first set, we do the principal component analysis on the independent variables, and these principal components are used as independent variables in the regression. So, why now we regress with the principal components, that is what we call as regression on principal components. What do we do in this? There are p variables, p independent variables here, and for each of the p variables you have number of values available with you. For example, I is the ith observation of the jth variable. So, you may have several variables j is equal to 1 to p variables you may have. The independent variables we standardize generally rather than just centering, because these independent variables may come with different units. Like I said, rainfall may be in depth units, soil moisture may be in percentage, area may be in area units and so on. So, to account for the different variables that come with different units, we standardize all of them. So, that you are writing it as x I j minus x bar j over s j. Now, the capitals and small are used interchangeably in regression as I mentioned earlier. So, do not worry too much about the capitals and the small, as long as you understand that this is the observed value of the ith observation and jth variable, and therefore, we are talking about the mean of the jth variable and the standard deviation of the jth variable. So, that is how you standardize all the independent variables. The dependent variable being a single variable, we can just use the centering. So, we call this as centering. This is the observed value for the dependent variable ith observation minus y bar. Y bar is the mean of the dependent variable. So, the dependent variable we center and independent variables we standardize, and then use the principal component analysis on the independent variables. Then the transform matrix Z, remember this is this defines our x, which is the independent variables or the transformed independent variables or the standardized independent variables if you wish, and these are the principal components. So, this is a matrix consisting of the eigenvectors. So, on this we get the transformed data Z. So, Z is transformed from the standardized data on the original independent variables, which is a p variables. So, this is a n by p matrix, and this is p by p matrix, because we are talking about the eigenvectors, and Z is again n by p matrix of the transformed data. Then we look at the dependent variable now. Let me explain that. You have the dependent variable, let us say this is the y matrix, which is n by 1 vectors, because there are n observations, and this is Z, which is a n by p matrix. So, this is n by 1 and this is n by p, and these are the coefficients of the regression. This is a coefficient matrix, and that is p by 1 vector of unknown parameters, and our aim in the regression is to determine these unknown parameters. Recall from the lecture before the previous one, where we discussed the multiple linear regression on how to obtain these unknown parameters for a multiple linear regression. Exactly the same procedure we follow here, and then obtain the betas. Now, in the scalar form it is written as y I is equal to j is equal to 1 to p summation beta j z I j. This is a scalar form of this matrix form. So, essentially we solve this now and then obtain beta. Z is known, y is observed values of the dependent variable, and therefore, we can obtain B, the matrix B. So, from your multiple linear regression, just compare this. How did we estimate B? In that case, in this case, when we are writing y is equal to z b, we write b cap, which is the estimated value of B, as z dash z inverse z dash y, where our z is this z now x a, this is z, and our y is n by 1. So, z is, let us look at the dimensions now. What is z? Z is n by p matrix. So, z is n by p. So, this is p by n z dash, and z is n by p, and therefore, you will get p by p, and z dash is again p by n, and this is n by 1. So, p by n, n by p. So, you get p by p here, inverse p by p, and then p by n, therefore, you get n by n and then n by 1. So, you will get n by 1. I am sorry, let us look at that. This is n by p, z is n by p matrix, and this is z dash is p by n. So, you will get p by p, and this is z dash is p by n. So, you will get p by p, p by n and n by 1. So, this will be p by 1, b dash will be p by 1. So, that is what you get here. This is beta 1, beta 2, beta 3 etcetera up to beta p. This is p by 1. This is a matrix that you obtain from this expression here. So, essentially we write y is equal to z into b, and then our aim is to obtain this b, and this is how we obtain b from this. Once these are fixed, that is these are obtained or these are estimated beta 1, beta 2 etcetera beta p, then your regression equation is in place. So, let us look at an example now. Here what we are doing is that let us say we have a basin where let us say this is a basin, and then you have the runoff values available here. Okay. And then these are several rain gauges. Let us look at this is rain gauge 1, rain gauge 2, rain gauge 3, 4 etcetera. A common method is in the hydrology that you get some averaged rain value and then relate it with the y here. But it may so happen that you would like to use all of these rain gauges independently. Let us say there is x 1 here, x 2, x 3, x 4 and so on. You may want to use all of them and then relate with the runoff at this location. So, we may want to write y as a function of x 1, x 2 etcetera x p. There are p independent variables. Okay. And then we want to estimate the runoff at this point, which also we call it as yield of this stream. Let us say there is a stream here, and then these are all the stream locations. So, this rainfall is contributing to runoff at this location, and this runoff we want to estimate based on the values here x 1, x 2, x 3, x 4 and so on. There may be p such rain gauges. Let us do this exercise. The first point to be noted here is that x 1 and x 4 may be correlated, x 1 and x 2 may be correlated, because they may come from the same hydrologic region. We are talking about this watershed here, and therefore, they may come from the same hydrologic region. This is a homogeneous hydrologic region, and therefore, the rainfall here and rainfall here and at all these locations may have significant correlations. And the other thing is that you may have so many rain gauges here that the size of the problem may become slightly unmanageable. If you are having let us say 10 variables, 12 variables and so on. Additionally, apart from the rain gauges, you may also have some other variables being put into the runoff estimation. For example, you may want to put in evapotranspiration, because from the rainfall part of it also goes as evapotranspiration, and therefore, you would like to account for that in the runoff that is observed. You have the observed values of y, let us say for the last 50 years every month you have the observed values. So, 600 values you may have. You have concurrent observed values on rainfall at this location, which gives x 1, rainfall at this location which gives x 2 and so on. For all the p variables, for all the p sites, you have the rainfall values observed concurrently with the runoff values. Now, we want to fit a regression equation of the type y is equal to f x 1 x 2 etcetera x p. We will use the principal component analysis and then fit this regression equation. So, on the principal component, for the principal component analysis, the first thing we do is to standardize the original data, that is on the independent variables, and also center the dependent variable data. Then we have to carry out the principal component analysis. How did we carry out the principal component analysis? Once you have the data matrix X, which is n values corresponding to each of the p variables, which means it is a n by p matrix, we calculate the covariance matrix from this. That means, covariance of p variables with p variables. So, we get a p by p matrix of covariances. On the p by p covariance matrix, which is a square matrix, we get the eigenvectors and the eigenvalues for the covariance matrix, and we use these eigenvectors as the principal components and then obtain the associated principal components for the covariance matrix, and then use the regression equation on these principal components. So, let us see how we do that in the example. So, you have rainfall, annual rainfall at 10 stations. So, these rainfall values we denote it as x 1, x 2, x 3 etcetera up to x 10. So, there are 10 stations. So, you have 10 variables associated with it. The observed annual yield associated with these 19 years of annual rainfall are also given. That means, this is annual rainfall and the associated annual yield. By yield, we assume you understand that it is a runoff at that particular location, which means that is the yield of that watershed, which is just the runoff that is observed. So, we have concurrent values for 19 years on the annual yield as well as on these 10 stations, which are taken as independent variables here. So, we want to obtain the prediction model for the yield associated with the rainfall. So, we want to develop a relationship between the annual yield and the rainfall in all these 10 stations. So, let us look at how the data is organized. We have 19 years of data. So, these are the annual values. So, this is the year number and the annual yield is given here for all the 19 values. This we take it as a dependent variable y, and these are all the rainfall values given at the 10 stations. So, at the 10 stations you have the associated rainfall values here. Now, both are given in millimeters units. What do I mean by runoff being in millimeters? That you have observed the runoff, let us say you have observed the volume of runoff divided by the total area of the catchment, you will get runoff in the depth units. So, all of these are in depth units. Now, as you can see, you may have a significant correlation between x 6 and x 9, for example, x 6 and x 10, x 2 and x 4 and so on. So, among these variables there may be some combinations of variables which have significant cross correlations. That means, they may be correlated with themselves. Now, such problems in regression are called as those of multicollinearity. That means, there is a significant correlation among two or more variables among the independent variables. So, this correlation needs to be addressed when we are developing a regression relationship. As I said, the first step is that we standardize all the independent variables and generate the vector x, which consists of the matrix x, which consists of the standardized independent variables, that will be p by n, which means 10 by 19. If you are, that is n by p, that is 19 into p variables. So, let us look at the regression equation now. All right, what we do is to demonstrate the utility or the usefulness of the principal components, first we will use all of these 10 variables as they are and develop a multiple linear regression between y and these 10 variables as they are. We will not do any principal component analysis to begin with. So, when we do that, we express y as x b. This is from your multiple linear regression. Y is a vector of 19 by n, there are 19 values and there is only one variable. So, 19 by n. X is a matrix of 19 values on 10 variables. So, this is 19 by 10 and b is a vector of unknown parameters and there are 10 such parameters, one associated with each of the variables. So, this is 10 by 1. So, you get beta cap as x dash x inverse x dash y. This is from your original regression. And so, you will get a regression of this type. We also introduce the intercept there. You just recall from your multiple linear regression. Then you get a expression of y a as a function of these 10 variables and you get the intercept as 782.4. To get the intercept, what you would have done is you would have put the first values of all the betas as 1, all the x 1 as 1. You just refer to the multiple linear regression to get this intercept and you get the coefficients beta 1, beta 2 etcetera up to beta 10 based on this equation here. Now, this is what we obtain when we regress the dependent variable on the independent variables as they are observed without doing any principal component analysis. As you can see here, all the 10 variables have been used and there are 10 regression coefficients here. If we use this regression equation as obtained here and we get the R square value, this is what we discussed in the previous lecture. R square value is given by b dash x dash y minus n y bar square, where y bar is the mean of the y data, by y dash y minus n y bar square. N is the number of data, x dash is the transpose of your x matrix, b dash is the transpose of b vector. So, when we do that, you get for this example R square as 0.988. So, this is this would have been nice and acceptable, provided this size was not big like 10 variables and provided we were sure that all of these are uncorrelated. For example, there is no correlation between x 1 and x 5, x 1 and x 4 and so on. So, all of these if they were uncorrelated and the size was not as large as this, then it would have been acceptable. But we would like to express this regression in terms of the principal components, where we derive a set of variables which are all uncorrelated and then we should be able to choose less than 10 number of variables, maybe 6, maybe 3, maybe 2 and so on. So, that is what we will try to achieve through the principal component analysis. So, what we do is we perform the principal component analysis now on the independent variables, that is x 1, x 2, x 3 etcetera, x 10. We will do the principal component analysis on that, then regress the y, which is the dependent variable, on the principal component analysis. So, the aim, as I mentioned, is to reduce the size of the problem and to account for correlations among the rainfall values at the 10 stations. But what do I mean by account for? It is not as if we are calculating the correlations and putting it into the regression. No, we want to convert the original set of independent variables which were all correlated among themselves to another set of variables which are uncorrelated among themselves, and that is what we mean by accounting for the correlations among the independent variables. And also do not get confused between the usage of word independent variables. They are independent in as much as they do not depend on the dependent variable. whereas the dependent variable depends on these variables and therefore, it is called, they are called as independent variables, but they may not be independent among themselves, and that is what leads to multicollinearity, as I mentioned. The multicollinearity, by multicollinearity I mean some of these variables that we are using in the regression are correlated with each other. Okay, to do that, then we have 10 stations and we have observations going from I is equal to 1 to 19 in this particular case. So, 19 years of data at 10 stations. So, that data x I j, we deduct x bar j at the jth station, you take out the mean of that jth station data and divide it by the standard deviation of the jth station data. That is, you take any station, the mean of this and the standard deviation of this you use to standardize the data at station number 6. That is what we do here, and so we obtain corresponding to each of the station, we obtain the n values, 19 values, which are all standardized values. And then the dependent variable y, we simply center it. We take the mean of this and then y minus y bar. So, we center all of these and obtain the dependent variable data. The mean of all of these stations are given here and the standard deviations, and of the dependent variable the mean is given here. The standard deviation is not necessary for y. So, we will use these means at this particular location. J is the station. So, j goes from 1 to 10 here, and I is the year of observation. So, you use for the jth station you use x j and s j here, standard deviation. Similarly, for y you use this mean 3569 as y bar, and you get the standardized annual rainfall and centered observed basin annual yield. So, this is centered values and these are standardized values. So, x 1 to x 10 you get the standardized values, and similarly these are the dependent variable centered values. Now, you focus on these sets of values now x 1 to x 10, you have 19 values associated with each of them. We will get the covariance, we will obtain the covariance matrix for these 10 variables in preparation for our principal component analysis. So, how do we obtain the covariance? Let us say these are the variables, I write them as let us say x 1, x 2 etcetera, x 10. Similarly, x 1, x 2 etcetera up to x 10. So, these are the variables. So, x 1 to x 1, that is a covariance, and x 1 to x 2 covariance, x 1 to x 3, and this is what we obtain here. On the standardized variables, remember we are talking about the standardized variables, and that is why you get the covariance x 1 as 1 itself, and this will be all diagonal elements will be 1 here. So, this covariance is x 1 to x 2. Let us say I want to compute the covariance between x 1 and x 2. It is given by x 1 I, 1 is the first variable, and for the ith period I is equal to 1 to n minus x 1 bar, x 2 I minus x 2 bar etcetera by n minus 1. N is 19 in this case. So, like this you form a 10 by 10 matrix. So, x 1 to x 10, similarly x 10 to x 10. So, you can get a 10 by 10 matrix, which is a square matrix, and for this square matrix we now obtain the eigenvalues and the eigenvectors. For obtaining the eigenvectors, first you have to get the eigenvalues. So, let us get the eigenvalues. If I denote this as the matrix S, the covariance matrix, we denote it as the matrix S here. and therefore, I should be able to get the eigenvectors and the eigenvalues corresponding to the matrix S. How do I get that? So, the eigenvalues are obtained by determinant S minus lambda I is equal to 0. I set it as determinant S minus lambda I is equal to 0 and then obtain lambdas here. S is a 10 by 10 matrix and therefore, I will get 10 lambda values here. So, the eigenvalues, this is obtained from the MATLAB routine. We get the eigenvalues as 4.95, 945 and so on. So, there are 10 eigenvalues that are obtained for the covariance matrix. We use these eigenvalues and associated with each of the eigenvalues we get one eigenvector, like that we get 10 eigenvectors. We use this S minus lambda I into x is equal to 0. This is a matrix and this is a matrix. So, we obtain the eigenvectors now. This is eigenvector number 1, eigenvector number 2, etcetera. So, this eigenvector is associated with this lambda 1, this eigenvector is associated with this eigenvalue lambda 2 and so on. So, associated with each of the eigenvector there is a eigenvalue. As I mentioned, they come in pairs. There is a eigenvalue and there is a associated eigenvector. So, this is what we obtain for the covariance matrix. Then we use these eigenvectors and look at the percentage variance explained by each of the eigenvectors. There are 10 such principal components. The eigenvectors consist of the principal components here. Okay, let us not get confused. This is principal component number 1, which is the eigenvector number 1, principal component number 2, number 3 and so on. There are 10 such values here. Now, we will see how much of percentage of variance is explained by the first eigenvector, the second eigenvector, third eigenvector and so on. To do that, we look at the eigenvalues, associated eigenvalues. Let us say this is lambda 1, lambda 2 and so on. So, I will get the percentage variance explained by this eigenvector by using the corresponding eigenvalue. So, I will get lambda j by trace S, where trace S is simply the summation of all the eigenvalues, that is S in this case will be this plus this plus this plus etcetera. So, I can write trace S, if you recall from your last lecture, as we will write trace S is equal to simply lambda j over j, all the eigenvalues, summation of all the eigenvalues, and we get the percentage variance explained by a particular eigenvector by using this on the associated lambda j. So, this says that the first eigenvector explains 49.447, second one explains 26.310 and so on. This is arranged in descending order. So, this is how we obtain the percentage explained by these various eigenvectors. Now, look at this. If we take the first 6 components, that is 49.447 plus 26.310 and so on. If you take first 6, about 95% of the variance is explained by the first 6 components. So, we have the option of developing the regression only using the first 6, because we are satisfied that 95% of the variance is explained by these 6 components. So, I can ignore the remaining 4. If you want to include all the 100% of variance, then all the 10 principal components have to be included. So, let us look at first the 6 components, that is I use only the first 6 eigenvectors and develop the relationship of the dependent variable on these 6 principal components. Essentially, this is the advantage, when we are using the principal components, we can see how much of percentage variance, or how much of information content is in fact captured by using these 6 hygiene vectors is the question that we are trying to answer. So, in this particular case we are saying that 95% of the information can be captured in terms of the variance. In terms of the variance, we can capture about 95% of the information by using these 6 components, and therefore, it is not necessary or you can afford to ignore the remaining 4 components. That is the interpretation here. So, we will use these 6 components and then regress the dependent variable on the 6 hygiene vectors now, or 6 principal components, so to say. So, what we are doing now, z is equal to x a is what we are saying, and a is the principal components, and we are using only the 6 principal components. So, a is a vector of 10 into 6, there are 6 principal components. Look at this now, the first column is the first hygiene vector, which is the first principal component, second principal component, third principal component, etc. Look at the hygiene vectors here. This is the first principal component, second principal component, up to 6 we go 1, 2, 3, 4, 5, 6, and these are the 6 principal components we are considering. And these 10 are associated with the 10 variables. So, you had initial 10 variables. So, you have got 10 values corresponding to that. Remember hygiene vectors, this dimension is p by p, which is 10 by 10. Out of that we are taking up to 6, therefore, we are taking 10 by 6 matrix here from this, and then using the principal using the regression relationship. And this is your original x value. By original x value, I mean it is a transformed x value, standardized x values. So, this comes from the standardized x values here, that is 0.172 minus 1.21. So, we use this entire data here after transforming, after standardizing, and then put the regression relationship. So, this is 0.172 minus 1.29. So, this is your 19 by 10 values, the matrix is 19 by 10 and this is 10 by 6. So, we obtain a matrix of 19 by 6 for Z, that will be n by p, and now this p is restricted to 6 now. So, this is the matrix Z we get, this is the transformed data, as after I do the multiplication x by a, when I do this I get the matrix Z as 19 by 6. Now, this one has to be regressed on the dependent variable y. What did we do now? We use the principal component analysis and transform the original data into Z. Now, we use this Z to regress on y. So, y will be regressed on this transformed data Z. So, we write y is equal to Z b, where y is the dependent variable and Z is this transformed data now, this matrix is obtained, and b is the vector of unknown parameters which we want to estimate. So, being a multiple regression, multiple linear regression, we have seen how to estimate b. So, we call it as b cap is equal to z dash z inverse z dash y, much the same way as we did for our multiple linear regression with the original variables, except that we are now using the transformed data. The transformed data is obtained from transforming the standardized values, standardized vector of matrix of standardized values of the independent variables, and multiplying that matrix with the principal components, and we have used 6 principal components associated with the 6 hygiene vectors, which explain about 95% of the variance in y. So, we know z, therefore, we can get z dash z inverse and z dash is obtained, and we know y, y is the centered values of the vector of the centered values of the dependent variable. So, we know y and therefore, we can get b dash. Now, b dash is the estimated values of the parameters beta 1, beta 2 etcetera, beta p. In this case, we get 6 beta values. So, z dash z inverse, this matrix z dash z inverse, I will give you directly. This is a 6 by 6 matrix and this is a symmetric matrix, diagonal symmetric matrix, and this is what you get here. And using this, we get b cap, which is the estimated values for betas as 6 by 1 matrix as 192.2 and so on. So, this is your beta 1, this is beta 2 and so on. So, we have now estimated the coefficients for the regression relationship beta 1, beta 2 etcetera, beta 6. And we can write the regression relationship now using this as if we do not have the intercept directly, we use all the 6 PCs. We write this as 192.156 PC 1 etcetera, PC 2, PC 3 and so on. This is your y. And the associated R square value we obtain as 0.978, which is slightly smaller than what we obtained earlier, which was 0.98 or some such thing. Now, there are two important things here, important aspects. We are writing y is equal to z b, and that in the long form we are writing this as y is equal to these are the beta 1, beta 2, beta 3 etcetera values. The PC 1, PC 2 etcetera are in fact the eigenvectors that we have obtained. These are the eigenvectors. Let us say you are looking at 6 values. I am sorry. So, let us look at the eigenvectors there. These are the eigenvectors. So, that is how we obtain a regression relationship on PCs, that is the principal components, which are essentially the eigenvectors. Now, there are some interesting features on this particular regression equation. You see, you obtained beta 1 as 192.16, beta 2 as this value and so on, by using 6 principal components, because we said that 95% of the variance has to be explained by this model, and therefore, I go up to 6 values. Let us say that I sacrifice some more information and not go up to 95%, but I will restrict myself to first 3 principal components alone. So, I may not be able to explain 95%, but maybe slightly smaller than that, let us say 85% or 86% and so on. And then discarding some other principal components, I redevelop the regression relationship. Let us say out of these 6, I redevelop discarding these 3 now. An interesting point here is that when we do that, these coefficients still remain the same. This is because they are orthogonal to each other. Remember, the principal components are orthogonal to each other, and that feature brings to the fore the fact that if you discard some of the beta values or some of the principal components and then redo the regression, your coefficients still will remain the same, and this is quite interesting. Let us look at that. These are your percentage explained from your earlier table. We used these are the percentage explained. So, we have arranged them in descending order. In fact, in this particular case it comes in the descending order. So, when we used 95% of the variance, we went up to the 6th principal component. So, we used all the 6 principal components. We use the same table now and look at only the first 3 principal components. So, the first 3 principal components explain 85% of the variance approximately. Let us say that I am satisfied with using 85% of the information. That means, I want to reproduce 85% of the information in terms of the variance, and therefore, I restrict my regression relationship only to these 3 principal components and develop the regression relationship again much the same way as I did just a while ago using all the 6 principal components. I do this now on these 3 principal components. So, we do the same thing, our X matrix remains the same and our A matrix now is restricted to only 3 variables. These are the 3 principal components. So, I will get a 10 by 3 matrix instead of the 10 by 6 that I got earlier. I use this transform data now and then z is equal to x into A. So, this is a z matrix, this will be 19 by 3 instead of the 19 by 6 that I got earlier. Then we develop the regression relationship, which is y is equal to z into B, and y is this remains unchanged and z is modified now, z is 10 by 3 now. So, I get beta cap as z dash z inverse z dash y. So, I get the beta cap z dash z inverse, the intermediate values are given. Look at this now, if we took only the first 3 components, I am getting the matrix up to this point. This is my first 3 components, whereas if I took all the 6 components, I would have got this matrix. So, this is just a subset of the earlier matrix. So, I get this principal components and then obtain the B cap, which is the estimated values for the parameters B as 192, 13.3 minus 33.3. Look at the earlier estimates now. These 3 components still remain the same. So, when I change my dimension, these have not got changed, these are just the same and I have just discarded these other remaining 3. Now, that is a interesting feature of the principal component. So, we can just ignore these 3 and then first use the first 3 in our regression relationship. So, the equation now is the first 3 coefficients only will come into picture and these 3 coefficients are exactly the same as we obtained earlier using the 6 components, and I obtain a R square value of 0.961, which is smaller than if I had used 6 components. So, if I used all the 10 variables in their original shape, I got some R square value, I got some regression relationship, R square values higher than the other 2. Then I reduced the size, I used 6 components, I got a R square value of 0.97 or some such thing. I reduced it further and then I get a R square value of 0.961. Now, this in some sense indicates the amount of information that can be reproduced by using this particular regression relationship. So, this is what we do in regression using the principal components. Now, there are certain advantages of doing this. As I just mentioned, let us say that you took 95% of the variance and then that is those eigenvectors which could reproduce 95% of the variance. In our example, it was 6. So, 6 of them you took and then obtained the regression relationship. On that, if you discard the 3, the remaining 3 coefficients still remain the same. That is the beauty of this. So, the numerical values of the betas as you obtain using large number of principal components will remain the same even if you discard some of them, some of the latter betas. And then the interpretation of the betas in terms of the independent variables is simplified now, because we are saying that these betas or these principal components that we are using in the regression relationship are explaining so much of the variance. But when we do this principal component analysis, even if we use let us say only 3 principal components in the regression relationship, still the complete observed data on all the 10 variables are necessary. This I keep on repeating, that the betas or the principal components that we are using now should not be related one to one with the original variables. These principal components are linear transformation of combination of all these 10 variables. And therefore, even if you use only 3 principal components, the original data must be available for all the 10 variables. So, that is a minor disadvantage. So, to conclude now, in today's lecture essentially we picked up on the principal component analysis that we discussed in the previous lecture and saw how we use the principal components in the regression relationship. So, essentially if you recall, the principal component analysis is done on the principal components are the eigenvectors which are obtained on the covariance matrix. So, if you had 10 variables, you have a 10 by 10 covariance matrix and on this you obtain the eigenvectors and these eigenvectors are in fact the principal components. So, for a 10 by 10 matrix you get 10 eigenvectors and each of these eigenvectors represents a principal component. And instead of doing your regression of the dependent variable on the original independent variables, we do the regression of the dependent variable on the principal components or the eigenvectors. This has the advantage that the eigenvectors are uncorrelated. So, the first eigenvector has no correlation with the second eigenvector and so on. And also we have the advantage that we can reduce the size of the regression. Instead of using 10 principal components or 10 variables, original variables, we may use just 6. In the example that we just saw, we used only 6 because the 6 eigenvectors explained or contributed to 95% of the variance in the original problem, original dependent variable. And thus, we can reduce the size depending on how much percentage the particular set of principal components can explain. In fact, in many realistic situations, we may have 20 variables, 30 variables and so on. Associated with that, we may have 20 eigenvectors, out of which only the first 3 may explain up to 90% or 95% of the variance, and therefore, you can afford to ignore all the remaining principal components and developing the relationship just based on the first 3 principal component. So, these are the advantages. Next, we move on to multivariate stochastic models. That means, we now know how to develop regression relationships based on multiple variables. We will extend this specifically to hydrologic problems where we are dealing with multiple variables and then we want to develop stochastic models on that. So, we will continue the discussion in the next lecture. Thank you for your attention.